Hey everybody, welcome to the last lecture in this lecture series. This is on section 6.4 in the textbook, and the topic is triple integrals. In this section, we're going to do some complicated mathematics. Triple integrals are complicated in general, but we're going to base everything on things that we've already learned in multivariable calculus, which ultimately go all the way back to what we learned in single variable calculus, how to capture the area under a graph using a single variable integral. So on the next couple slides, we're going to slowly build this up and build up our intuition for what a triple integral could possibly even mean. We'll learn how to set up triple integrals over three-dimensional regions, which might not just be rectangular prisms. These will be the three-dimensional and higher version of our rectangular regions from double integrals. And ultimately, we'll learn some techniques to evaluate triple integrals. These, again, are complicated. It may not be the most complicated math we've done in the class, but for my money, it's one of the harder sections. So we'll end on this, but we're going to end on a high note and learn something pretty cool, which is how to capture higher dimensional measurements than just area and volume using integration. So to get started, we know how to form a higher dimensional function. So far, we've been integrating in our double integrals functions f of two variables, x and y, but we know we can write down functions of a higher number of variables, let's say x, y, and z. Given such a function, what does it mean to integrate this function, or what can we measure about this function? Well, if you think about it, a function of three variables assigns an output number, a fourth variable, to every input in three-dimensional space. And if we want to keep track of the values of that function, now we can't say height, but we could say the fourth dimensional measurement of that function over some three-dimensional region. We can actually use a notion of triple integral to capture this. And you should probably pause the video now and sketch out at least your favorite looking function in 1 and 2 dimensions, namely a one variable function and then a two variable function, maybe with some level curves or just a quick sketch of the XY plane region that it's over. And think about what it means to integrate those functions. For one variable function, integrating the function with respect to dx, if it's a function of x, will return the area, or in general, the signed area under that function. While an integral over some region in the xy plane of a two variable function will tell you about the volume underneath, and in general, the signed volume underneath the graph of that function in three dimensions. If we have a three variable function, what we're asking for is some measurement, something higher than length, area, and volume, which sometimes is called hypervolume or four-dimensional volume, that captures the entire measurement of that function inside of a three-dimensional region. So here's how we're going to compute this. We'll first start with an approximate way to do it. If we have a three-dimensional region in XYZ space, let's call it D, we can subdivide D into smaller regions. If we let VI be the volume, which is a measurement of a three-dimensional region, the volume of the ith region in our subdivision, and inside of each of these little subregions, we'll choose a point, just like the midpoint of our rectangles and our rectangular prisms. We can use the diameter of the largest region and shrink it down to get a limit formula for a triple integral. And here's how we're going to define it. The triple integral of f over the region D in XYZ space is going to be the following limit. We'll write it using three integral symbols to denote that there are three variables being integrated over D of f. And the differential here, dv, denotes the differential with respect to volume, whereas previously dA was for area in two variables. And here's the first definition that we'll give, although we'll have an easier to work with definition in a moment. We can compute this as a limit as the largest region shrinks down to zero volume, or the diameter shrinks down to zero, of the sum of the volumes of each of the, sum of the hypervolumes of each of the subregions. So I'm going to start from the right. VI, again, was the volume of the ith region in our subdivision. And then we're going to multiply that by its fourth dimensional measurement, namely the height in the fourth direction, or f, the output of that midpoint or whatever point we choose in the region VI. We'll plug that into the function to get a fourth measurement. It's really hard to draw these because we, as humans, can't really perceive things in 4 dimensions. It's already hard to draw in 3 dimensions on a 2-dimensional slide. But this is the same notion that we did to compute rectangular areas and sum those and take a limit to get a single variable definite integral. And in this class, to get a double integral, we summed base areas times height in order to get a 3-dimensional volume measurement. Here we're getting something 4-dimensional, a 3-dimensional volume times another 1-dimensional output of a function. how could we possibly compute these? It's already difficult to compute the two-dimensional area limits, or what ends up being the sum of volumes of rectangular prisms. And it's a nightmare if I can't even draw these rectangular prisms. But Fubini's theorem is actually a really useful idea that will help us to compute triple integrals. We're going to write them, there's a typo on the slide, but we're going to write them as iterated integrals. If you delete that C, that's the right word. And the theorem, which is some version of Fubini's theorem that tells us about how to write the bounds and how to split things up, is that if we have a triple integral over some region D of a function f of x, y, z with respect to volume, that's the dv, then we're going to integrate 3 times an iterated integral with respect to each variable, where x1 and x2 are the x bounds, y1 and y2 are the y bounds, z1 and z2 are the z bounds. This d shouldn't be here. This is just a typo from the previous formula. We're going to integrate the function f of x, y, z with respect to, in this order, z, then y, then x. So interpreting things as hypervolumes or 4-dimensional volumes seems intimidating at first, but when we get good at iterated integration, even just for double integrals, the next logical step is just to throw on another integral symbol, compute some bounds for that new integral symbol, and then just crank through an extra step of an iterated integral. We're integrating with respect to one variable at a time, and there's nothing stopping us from doing this. So Fubini's theorem really says not so much that this is the correct formula, although this is true and requires a little bit of calculus to prove, but more importantly, that the variables can be reordered as long as we carefully keep track of the bounds and reassign them different values depending on which variables are integrated out first. I want to point something out. We'll see this in a couple examples in a moment, that on the very outside integral, in this case x, but after reordering it could be any of the 3, we have to have constant bounds, because when the other variables are integrated out, we'll just be left with a single variable function. So the outer bounds have to be constants to integrate over an interval. The y bounds, just like with double integrals, can be functions of x, but not of any other variables. And the z bounds can be functions of x or y because they still haven't been integrated, or in other words, those are constants with respect to z. So these can get really complicated because the outer bounds are constants, that's fine. The y bounds are functions of x potentially, and we know how to handle those, but the z bounds can be multivariable functions themselves. These are going to get pretty complicated pretty quickly. The key with these is to do things one step at a time, pause when you need to, get up and stretch, and then do the next step. And some of these can really take a long time, but that's the nature of calculus. It may take a long time, but it will give you an answer in the end if you do things carefully. So let's see an example of a triple integral, and this time we'll do it over a rectangular prism region. Remember that our regions that we're integrating over in this video are 3-dimensional regions, and the output of that calculation will tell you a 4-dimensional volume or a hypervolume of some 3-dimensional function over that 3-dimensional region. So if we're given this rectangular prism R with x, y, and z bounds given as shown in the brackets, let's compute the triple integral of this 3-variable function with respect to volume. Because you've probably been doing a lot of double integral practice, this one should not be too much harder than the ones that we've done together or the ones that you've been doing on your own so far. So if you'd like to pause the video and just try to work through this yourself, try to get a feel for what the notation adds to the picture with 3 different integral symbols, I encourage you to pause and try this now. I'm going to pick up right at the start of the problem, and let's put in the correct integral bounds. And I chose an order for our differentials to integrate in this order. I'm going to do z first on the inside, then y, then x last. And this means that I need to go outside in to write down my integral bounds. So the x variable is ranging from 0 to 4, and I'm reading this all off of the description up here for the region R. The y variable is going to range from 0 to 2, and the z variable finally ranges from 0 to 3. And now we're going to start on the inside and work our way outward, performing each step as a single variable integral with the other variables held constant. So first of all, I'm going to keep my dy and dx integrals the same on the outside, and I'm going to perform a dz integral here. Every time I see a z, I need to integrate, and if I don't see a z, that means that that's a constant and we need to introduce a z. So the first expression, 3y is a constant, but z is a variable, becomes, we'll get a z squared, and we have to divide by 2. So I'm going to capture all of the constants out front. I'm going to keep y here because it's constant, and then I'll have a new z squared to deal with. On the other hand, x squared is a constant, so when we integrate a constant, we just get 1 factor of z. And here I'm integrating from z equals 0 to z equals 3. And just like I did with double integrals, I'm going to keep track of what I'm about to plug in by writing the variable equals that expression. This will be especially important when we have functions in our integral bounds in the next couple examples. So I'm keeping my first two integral symbols as is because we're not dealing with them yet. And in this step, I'm going to evaluate by plugging in z equals 3 and z equals 0. First of all, notice that z equals 0 makes every term 0, so I'm just not going to write that at all to save some space. When z equals 3, if we plug that in, I'll get 3 squared is 9, and I'll collect my coefficients to get a 27 over 2. And then we're just left with the y variable in the first term. On the other hand, x squared times 3, that's just going to be 3x squared. We still have a dy and a dx. And let's pause and take stock. That started with a complicated triple integral expression. But now we've performed one step of calculus. We did one integral and evaluated at the z bounds on the inner integral symbol. And we're left with a double integral. And this is just what we've been practicing for the last lecture or two. This is really one of those rectangular region integrals. And that's why we started with the rectangular prism at the start of the problem. But now we're just down to a single volume calculation. So we could say that the hypervolume of the original region, integrating the triple variable function f shown here over that three-dimensional rectangular prism, is the same as the volume of the region in the xy plane underneath the function shown here. But that's just sort of a consequence of the first step of calculation. This isn't necessarily how you can phrase things in general. Okay, let's do the next step. I'm going to perform a dy integral. So I need to keep my x stuff the same on the outside. When I integrate y, I'm going to pick up another 2 in the denominator, and then y jumps up to y squared. 3x squared is a constant, so I'll just pick up a single y, and I'm going to remind myself I'm plugging in y equals 0, y equals 2. And now things are looking a lot simpler and close to the finish line. So let's just wrap this one up together. If I plug in y equals 0 everywhere, you get 0, so we just need to plug in 2. And let's see, those cancel. 27 plus 6x squared. And now we're down to a single variable integral. I'll give you this integral. I'll do this one for you, but in the future, I may leave these for you to do at the end, since this is really just review from single variable calculus. We don't need the bounds. Let's do the integral. 27x plus 2x cubed, x equals 0 to 4. Let's see, 4 times 27. Oh, I think that's 108. And x, let's see, 4 cubed is 64 times 2 is 128. And if I plug in 0, I again get 0 everywhere. So this one didn't have too many extra parentheses or anything. In this case, we'll get, let's see, 236. So again, just for a moment of interpretation, in this problem, we were given a 3-variable function, 3zy plus x squared. And to every point in x, y, z space, this function assigns a 4th dimensional output. It assigns some measurement. And if we treat that as some 4-dimensional height in our 3-dimensional region, and we integrate over this rectangular prism region, we're really capturing the 4-dimensional volume or the hypervolume of this region. Now, of course, it's a signed hypervolume, but in this case, all of the outputs are positive given the x, y, and z bounds. So the number 236 is the hypervolume of that of the region underneath, or sort of captured by that function over the 3-dimensional rectangular prism that we started with. Great. How did that feel? Is it easier to compute these things or to visualize them? I suspect that you have a preference for one of the other, but sometimes computing things can be complicated as well. And I'll just say that my personal preference is to get a triple integral symbol in front of me and then just go ahead and crack through the calculus and the algebra and not worry so much about the visual after that. And the reason is if I tacked on a few extra integrals and had a sextuple integral, that would mean some geometric 6-dimensional volume maybe, but I really don't have a brain that can handle that sort of visualization. But instead I can do the algebra and just get a number as an answer at the end. And that's what these types of integrals are good for. All right, how do we interpret triple integrals? Speaking of things that I have trouble visualizing, Let's break our triple integral down into pieces. If we look at the inside of a triple integral, such as in the previous problem, just the integral with respect to dz with our z bounds, we can think of this as integrating away z and just leaving two variables behind. And what this is really doing is, if we look at the graph of the function w equals f of x, y, z, this is some three-dimensional figure in four-dimensional space. So it's really hard to visualize. But if we chop this figure, this three-dimensional figure, with a plane given by choosing, fixing any x and y coordinates in four-dimensional space, that'll determine a plane in 4 dimensions. Then we can compute the resulting cross-section of this four-dimensional region, or really a cross set. I'll still call it a cross-section though, slicing by a plane, and compute the area of that cross-section. It's now not a curve since we're 1 dimension higher, it's a surface, and computing the surface of that cross-section, the area of that cross-sectional surface of w equals f will give us the value of this integral. And we can vary the x and y that we put into this formula, and that will give us different cross-sections, and each of those cross-sections has a different area. This picture sort of captures what's going on. It's really hard to visualize. But if you were to imagine, imagine taking the graph of w equals f of x, y, z, fixing some x and y and slicing through the surface, you'd have a two-dimensional slice, which would have an area, and it would look something like this gold plate here. Now, this blue rectangular prism is really some three-dimensional shadow of the four-dimensional figure given by w equals f of x, y, z. So you can imagine this is just like looking from one angle at the graph of this four-dimensional shape. But if we slice through it with the plane, then we'd get something like this gold leaf here. And I know this doesn't look like a plane, but remember, we're slicing through in 4 dimensions, and things will look funky in 3 dimensions. And in any case, if we move around the x and y coordinates, let's say down here in the xy plane, and then slice according to that choice of coordinates, we'll get different cross sections, different little gold leaves in different areas accordingly. All right, let's go one step up. If a single variable integral on the inside, integrating with respect to z, represents calculating a particular area of a cross section of this 4-dimensional function, or this 4-dimensional graph of a 3-dimensional function, then integrating z and then y will leave behind a function of x. And what does this function really tell us? Well, if we choose an x coordinate, and then we take the resulting cross section of our 3-dimensional figure in 4 dimensions, the graph of the function f, what we'll get is not a level set anymore, or a cross section that's a surface. We'll get a 3-dimensional cross section of that shape. And that 3-dimensional cross section is going to have a volume. So you can imagine taking that little gold leaf that had an area and spreading it out in the y direction, allowing for any possible y values ranging over the given region that we're integrating over. In this case, if we allow z to go from 0 to 3, that's going to give us that gold leaf, and allow y to range from 0 to 2, that's going to swing us in this direction and really cut out a 3-dimensional family of gold leaves, which total together to give us a 3-dimensional shape with a 3-dimensional volume. For every x value that we choose, let's say right here on the x-axis, this will automatically cut out a 3-dimensional cross-sectional figure that has a volume. And this double integral, just with respect to z and then y, describes the volume in yzw space, or in some 3-dimensional shadow of 4-dimensional xyzw space. And this is a function of x. So as we slide x around to choose different x coordinates to plug in, we will get different volumes. And then the question is, what happens when we do the last integral with respect to x? Well, I definitely can't draw it, and it's even hard to say in words. But what we'll do is look at all of these possible 3-dimensional kind of warped cube shapes here over all possible values of x inside of our range of x values. In the problem, it was 0 to 4, I think. Now I'm forgetting. But we'll slide our x value through, and then we'll just add up all of those volumes. And if we add up a bunch of volumes, that turns into a 4-dimensional or hypervolume in the end. That's the best we can do for now. Here's a takeaway from triple integrals. These are actually really useful in other sciences that use calculus for some of their calculations. If we have a function that tells us about the density of an object, That's one way to assign a new value to every point in XYZ space. Tell me the density of the material at that three-dimensional coordinate XYZ. And if we integrate a density function, this will actually give us the mass of the object. So computing a triple integral of a density function over a three-dimensional region tells us about the mass. See if you can reason through the analog one dimension down, where integrating a density function over a two-dimensional region tells us something about the mass of that two-dimensional region. Mass doesn't quite make sense in 2 dimensions. We really need 3 dimensions to make sense of it, but there's some analog for you to think about there. Likewise, if we integrate the 3 functions x times the density, y times the density, and z times the density, these will give us 3 different measurements. And it turns out if we put all of those 3 measurements together into 3 coordinates, those 3 coordinates describe the center of mass of the object. So triple integrals not only tell you the total mass of an object, but they can be used to extract the center of mass of an object. This is really powerful. It's already a difficult problem in 2 dimensions, but it's extremely valuable in 3 dimensions to have a computational tool for finding center of mass. Likewise, we won't do any 3-dimensional probability problems. We reached our limit last section of two variables at a time. But if we had 3 different potentially independent random variables, x, y, and z, then a probability distribution, a joint probability distribution for those 3 different variables would be a 3-dimensional function. And in order to compute the probability that x, y, and z satisfy certain conditions, that they're within certain regions of 3-dimensional space, we'd have to compute a triple integral to evaluate probabilities. And that's exactly what's done in practice. With a higher dimensional space, you'll need a higher dimensional probability space with more numbers of continuous variables. You will need higher order iterated integrals to compute probability. And in practice, this is exactly how complicated, sophisticated, high dimensional statistics are performed. Finally, just like we saw in a couple lectures ago with our double integrals that compute area, integrating the constant function 1 with respect to volume over a 3-dimensional region will always tell you the volume of that region. And you can think of this like assigning a 4-dimensional height of 1 at every point in 3 dimensions. And a 4-dimensional volume is the 3-dimensional base volume times the 4th dimensional height. And if you don't like thinking about that, you can just take this as a fact that the triple integral of 1 dv is equal to the volume of the region that you integrate over. So to put things back together, density is really a good way to visualize what's going on and not have to think about some 4th dimension of actual space. Another way to think about the 4th dimension instead of density could be something like temperature, and you're trying to capture the total temperature of a region, the total temperature happening on some hot plate. But imagine this being a 3-dimensional hot plate with some width to it. The first integral on the inside with respect to z is going to compute the total density of each of the vertical segments by choosing any x and y coordinates. For example, here, if I choose an xy coordinate in the xy plane and extend upward in the z direction within our region of integration, this rectangular prism in this case, then the total density of the space here will be captured by the integral along this strip, and that's what the first integral tells us. Next, the double integral over z and then y is going to capture the density of any rectangular slice of our 3-dimensional region. So the object here may not have uniform density over the entire rectangular prism. It may vary depending on where we are in the prism. And each of these blue slices will capture some 2-dimensional region of the 3-dimensional prism. And you can total up a density by integrating with respect to z and then y, or by Fubini's theorem, vice versa. Finally, to compute the total mass of the prism, we want to add up the density of every particle inside of this region in 3-dimensional space. And that's done by computing the total triple integral with respect to all 3 variables. It turns out, and this might make you a little sad at the start, but this is actually really the power of triple integrals. It turns out that we can do some crazy things, just as we did with double integrals, and integrate over regions that are not just rectangular. In the previous double integral setup, we didn't want to just integrate over rectangular regions in the xy plane. Here in 3-dimensional land with a 3-dimensional function, we don't want to just integrate over rectangular prisms. We certainly have more interesting regions that we can integrate over. And here's an example. Let's take a look at the region R that lives above the xy plane in 3 space, below the cylinder given by this formula. And you can see this is the top half of that cylinder above the xy plane, and between the y values of 0 and 3. Let's first set up a triple integral of this function with respect to volume over this region. the function being 4 times y times z. And you can think of this as assigning a density value to every point inside of this semi-cylindrical region. And it's going to be not just the surface of the cylinder, but all of the points in between, ranging over all of these z values. And we want to compute the total mass of this object. Maybe this is some washer that we chopped in half or something, something with a little more variable volume given by 4 times y times z. So here it is. We've got our picture. Let's go set up an integral that describes the picture. And the first step I'm going to do, and I encourage you to do this every time you set up a triple integral for yourself, is to write down what the x, y, and z bounds are separately, just to think about them individually. If we're going to integrate with respect to z, then y, then x at the end, I think the right order, in my experience, is to start with the easy ones, those constant bounds on the outside, and work our way in to writing down the complicated inner integral bounds. So for the x bounds, let's look at the picture. What do the x bounds range over? Well, all I'm told is that x squared plus z squared is equal to 16. And you could think of this in the xz plane as the circle. I'm just going to draw the top half of it. It would extend down below as well. The circle in the xz plane centered at the origin. Here's the origin in the xz plane, and with radius 4. This is a familiar circle equation. But you have to picture it up on the wall in the xz plane. And if that's the case, then the x bounds range. What are the x bounds? The extreme points of a circle of radius 4 are plus or minus 4 in that coordinate. So in this case, x equals minus 4 to x equals positive 4 will give us our constant bounds on the outside of an integral. I'm just going to plug those in right now. And now we don't have to worry about the first piece. How about the y bounds? If we look carefully at the picture, y is ranging in this direction. We're actually told y bounds, but let's just double check geometrically that this makes sense. If we range from y equals 0 to y equals 4, given any x choice, this is going to capture the entire shadow of this three-dimensional region down here in the xy plane. And that's exactly what this appears to be. It's a rectangular region of the xy plane. And sure enough, ranging from 0 to 3, and just looking at the x and y parts together describes a rectangular region. This is the cross-section of the cylinder when we slice by the xy plane. Finally, the z bounds. The z bounds are a little annoying, but you can see it's sort of small here in gold. This z coordinate here is just solving for z in this xz equation, and it's 16 minus x squared, and take the square root. And notice that I don't have plus or minus this because we're looking at the region above the xy plane, not below. So we just need the positive half of the semicircle, or the positive semicircle, positive half of the equation. So the z bounds are going to be from, well, the floor is the xy plane, that's z equals 0, up to the height on this semi-cylinder, which is the square root of 16 minus x squared. Here's 3 different sets of bounds. Oh, I didn't plug in the y bounds. That's going to go from 0 to 3. And the z bounds are going to go from 0 up to this expression. And never fear, we have a function of x, and theoretically it could have been a function of x and y in one of our integral bounds. But we're just going to carefully go through each step, evaluating one variable at a time using an integral, plugging in the bounds, and reducing the number of variables in every step. So I'm going to get rid of the picture, the bounds. We're just going to focus on evaluating this triple integral symbol. Let's go step by step. And by the way, if you feel pretty ambitious and you want to try your first non-rectangular prism triple integral on your own, then pause the video now, give it a shot. The hardest step is at the start, just doing the z integral, and after that, things get easier. So I'm going to go ahead and integrate this function 4yz with respect to z. Z gives us a z squared, and dividing by the new power will cancel out power of 2. And I'm evaluating this from z equals 0 up to z equals the square root of 16 minus x squared. And then we'll have a dy and a dx integral to perform later, but let's just evaluate at these z bounds. 0 to 3. It's going to be pretty nice because when I plug in this square root expression, z is going to square it, and I'll get 2 times y times just what's under the radical raised to the 1. If I plug in z equals 0, that gives me 0 for the whole expression. So we're done, at least with the dz integral. Notice that we dropped one variable out by integrating it out. We're down to a double integral of a 2-dimensional function. And actually, we have a lot of tricks at our disposal. Notice that this function is factorizable. there's a y part and an x part. We could call these f of x and g of y. And one of our theorems from double integral land tells us that when we're over a rectangle, and sure enough, we're over a rectangle, we can split this into two single variable integrals and multiply them later. So let's take the x part, 16 minus x squared, integrate over the x bounds, multiply by the y bounds, 2 times y. Now you should be able to crank through this. It's two separate integrals, do them separately and combine them at the end. I'm just going to do them side by side and multiply them. Integrating with respect to x gives me 16x minus 1/3 x cubed, evaluated from -4 to 4. And 2y is going to give me 2/3. Oh, sorry, no, not 2/3. It's going to cancel out the 2, give me a y squared from 0 to 3. Let's plug in our values carefully. So if I plug in 4, I'll get 16 times 4 is 64. 4 cubed is also 64, by the way, over 3. And if I plug in -4, I'm actually going to get the same thing with negative signs. So this won't cancel out to 0, just to be clear. It's actually going to double the first expression, but let's just write it out this way. Here we go. That's the x stuff taken care of. The y stuff is easy. I'll get 3 squared is 9, minus 0. I'm not even going to write it. Okay, so here we're going to have 64 twice. That's 128. And negative 64 over 3 twice. That's negative 128 over 3. Solve this times 9. And let's see, 128, 3 of them is whatever it is, but subtracting away one of them would give me 2 128s, or 256 over 3 times 9. Canceling out a power of 3, I get 256 times 3, which, let's see, that's 768, I'm pretty sure. So quick gut check, we had this semicircular region in XYZ space. And we wanted to know the density of this, the total mass of this, where the density function assigns a density of 4yz at a coordinate xyz inside of this cylinder. And the total density, or the total mass, was 768 cubic units, whatever it is, or mass units. Great. There we go. That's our first irregular region. Let's see what else we can do. So here's some main takeaways. And this is a good approach in general to compute a double or a triple integral. The same logic here will apply one dimension down. So except for having z bounds, those won't happen in double integrals. So if you have a double integral and you can somehow visualize it or reason through the bounds that are given to see that there's a top surface and a bottom surface, then the z bounds can be given by equations z equals f of xy and z equals g of xy, describing those top and bottom surfaces. So again, z is going to be multivariable functions because it may depend on the other variables. These are used to describe the top and bottom surfaces that bound the region. Next, the intersections of those top and bottom surfaces can be used to produce relations on the x and y bounds. And in general, we can graph these by setting f and g equal to each other and getting equations of x and y, and graphing this as a curve in just xy space, or the xy plane. Any bounds that are given in terms of x and y separately from the intersections of these two surfaces can be used as well. Like in the previous problem, we didn't go below the xy plane because we were told not to. Finally, after drawing the boundary region in the xy plane, we can proceed to find x and y bounds just as we did by computing, or in order to compute a double integral, just by looking at the xyz or the xy plot of the base region. But here we have to actually get down to that place by doing something with z first. And notice that in the previous problem, I went backwards and I started with x, then y, and then z, but that was only because I had a picture to look at. And if I didn't have that picture, I would somehow have to produce a picture in the xy plane using the z bounds that are given. The cylinder has an equation, the xy plane is z equals 0, and I can use that to come up with bounds for x and y. And just like with double integrals, if we have top and bottom surfaces switching order, we need to break the region into smaller pieces. And we also may want to reorder our differentials in order to make the triple integral function on the inside easier to integrate. And in that case, we need to carefully reimagine and reorder the bounds that we're computing. The same procedure will apply starting with the first variable that you want to integrate in place of z, and then proceeding to the other two and graphing in their plane. Well, here's another problem to think about. Suppose we want to integrate some 3-variable function f, which we won't specify, over a region T in 3 dimensions, which is given by the tetrahedron or pyramid that has these 4 vertices. In general, specifying 4 non-coplanar vertices in 3 dimensions will give you a tetrahedron, which looks like a pyramid, and I'll show you a picture of this in a moment. How would we set up the bounds of integration, even if we don't know the function f? Well, here are the pictures, and I'm just immediately going to go jump to the tablet to show you how to assign integral bounds. I'm going to go x bounds, y bounds, z bounds again in this case. And the reason is I can draw some pictures and I can start with x bounds, but the procedure 1 slide ago told us if you don't have any pictures involved, or you can't produce pictures yourself, then start with the z bounds and try to get down to x and y bounds from that, and then build back up to the full triple integral. So let's start with writing down our drawing our tetrahedron in 3-dimensional space. That's the figure on the left, and looking at its shadow in the xy plane. Well, the xy plane is just going to give us a triangle. The 3 of the 4 points lie in the xy plane already. And with different tetrahedra, with different sets of 4 points, you may have to project things down just to their x and y coordinates. That'll still give you a shadow in the xy plane shown in the figure on the right. Now, in this figure, if we're going to integrate with respect to x last, let's just look at the range of x values that describe this figure. It's now just a triangle. The x bounds go from the origin has x coordinate 0 up to the given, or one of the bounds, which is 4, 0, 0, which has x coordinate 4. So we're going to integrate from x equals 0 to x equals 4 for the x bound. And those are going to go on the outside because they're constant. Let's think about the y bound now. We're not going over some rectangular prism region. And even with respect to x and y, we're not integrating over a rectangle like this. So we need to have a function, y as a function of x, in order to write down here. And it'll be a top minus a bottom. The bottom is the x-axis, which is y equals 0. And the top is a positively sloped line. So y, and it passes through the origin. This will be y equals mx. The slope here is if we rise by 2 to go from 0, 0 up to 4, comma 2, we run by 4. So rise over run 2 over 4 gives us 1/2 x. And if you want, you can go label this. This is y equals 1/2 x. And that we'll use for our top y bound. Now let's go to the z bounds. We need to look at, for any given point x, y in the xy plane, we want to see how the z values range inside of this 3-dimensional tetrahedron. Well, depending on if we're over here where we don't range by much, or the height is small, versus if we're over here and the height is large and close to 4, it's going to depend on the xy coordinate that we choose, how much height we're allowed to fit in. And the right way to do this is notice that this surface of the tetrahedron, this one face, is really the cross section of some figure given by slicing by a plane. This is part of a plane here. And which plane is it? And notice that the bottom of the figure is the xy plane, that's z equals 0. Which plane is it? Well, it's going to be z equals mx x, let's see, mx x minus an x coordinate. I'm going to use the point 402. No, I'm going to use the point 420. X minus 4 plus my y minus 2, and then the z coordinate here is 0. That's the coordinate I'm using. Let's determine what the slopes are by plugging in any other point on this plane. Oh, you know what? I could have used the origin actually. So yeah, I'm going to make things a little bit cleaner. I totally missed the fact that the origin is a point here. So the origin being a point means we can use x, y, and z coordinates 0, 0, 0, and just get a plane equation looking like this. By plugging in any other point, such as 4, 2, 0, we can deduce what these coordinates are. Hopefully, we might need 2 points to plug in, and that's probably what's going to happen. So if I plug in 4, 2, 0, I'll get 0 equals 4mx plus 2my. And that's actually not enough information to deduce anything about these equations. Let's use the third point, 402. Plug that in, we're going to get 2 equals 4mx plus 0my. And that's going to allow us to get all of the slopes and finally get a top equation for this expression. So let's do it. Let's see, mx is equal to 1/2 my. Need to solve for my. Let's see, my is equal to -2mx, it looks like. That's going to be -1. And that means the z bounds are going to be z equals 0 up to z equals 1/2 x minus y. Let's see if we can write down the triple integral describing this entire problem. The x bounds on the outside will go from 0 to 4. The y bounds, we said, went from 0 to 1/2 x. The z bounds, now we're from 0 up to a multivariable function, 1/2 x minus y, and the function was unknown. Who knows what it is? F of x, y, z, dz on the inside, dy, dx. As an exercise, I'm just going to tack this onto the end of this problem. Just to practice computing another triple integral, compute with the previous problem's density function for z, y, or 4 times y times z, whatever it was. So I'll give you one more problem to practice. We'll see a few more examples in this video, but I'm not going to work any more out. I'll leave those as exercises, and we'll do a few of them together in class. All right, so let's get back to it. We've got a few more topics with triple integrals before we end this discussion and end everything we've learned in this class. So one thing that's useful, a really useful trick, especially when we have more numbers of variables floating around, is the switching the order of integration trick. We may not always want to integrate z, then y, then x, depending on how our figure in three-dimensional space looks. For example, suppose D is the bounded region enclosed between the graph of 4x squared plus z squared, or y equals 4x squared plus z squared, which you should think of as a positive y direction opening parabola, but in 3 dimensions, so it's something called a paraboloid, and the plane y equals 4. Just a point on the picture, the surface given by y equals 4x squared plus z squared opens to the right, looks like a parabola in either direction if we take slices, and it's cut off at the value y equals 4. That's this plane that slices over here. And the question asks you to set up the bounds of integration for a triple integral of some function over this region. And in general, this is going to be difficult, but rather than choosing z to integrate first, why don't we look at the most complicated expressions here are the paraboloid, y equals a function of x and z, and then y equals 4 here. It's not so complicated, but they're both solved for y. So let's stick dy on the inside integral, and then go back a few slides and look at the procedure to see if you can find a shadow of this in the xz plane, and use an explicit formula or description of that shadow in the xz plane to come up with bounds for x and z. And it will be your choice to integrate with respect to x or z next, and you may get different setups depending on which one you choose to go with. I'll leave this as an exercise, but we will do this one in the classwork together. Just like we had with double integrals, sometimes it's possible to split a triple integral into a product of single variable integrals. And the same requirements are true. If we're integrating dz, then dy, then dx, we already know that the x values on the integral symbol are constants. But if the y and z bounds are also all constants, and our triple variable function on the inside can be factored as 3 single variable functions, f of x, g of y, and h of z, then we can split up this triple integral into the product of 3 single variable integrals, each of the variables with respect to their own variable bounds. We also have sum and constant multiple rules, just like we had for double integrals. And I'm not going to write those, but here's an example that you can pause the video and track through to see how we can split up an integrand, this is our f of x, y, z from a few problems ago, into separate pieces, each of which can be factored into products of single variable integrals. I'm not going to talk through this slide, but you can pause and look through what happens in each step if you like. And finally, here's some summary questions, and I'm going to leave you with a couple practice problems after these. What does Fubini's theorem say about integrals with the symbol dv in it? And what does dv even represent? Next, how can you use density to understand a triple integral? Why wasn't it necessary or even appropriate to use density to understand double integrals? Next, how do you find the bounds of the innermost variable in a triple integral? In many of our examples, it was dz on the inside, but in general, like the paraboloid problem 2 slides ago, you may want to use a different variable. And finally, how do you find the bounds of the other 2 variables once you've chosen the bounds for the inner variable in your triple integral? Here's another triple integral computation where in this case, you're not given a picture, you're given all of the bounding functions, and this is enough information to come up with bounds for the triple integral of some function g of x, y, z. If you want to practice actually computing a triple integral after you set this up, then, well, you can choose your favorite 3-variable function g of x, y, z if you like, or if you just want one that's already given to you, use the same density function 4 times y times z that I used for a couple slides. Here's a picture of the region in the previous problem, and this is in the slide, so you can look at this while you're thinking about the practice problem. Finally, here's another problem discussing the validity of a given setup for a triple integral. And given the region described by the inequality x squared plus y squared plus z squared is less than or equal to 25, is Chang's setup for this triple integral of some function f over that region a valid setup for a triple integral? Why or why not? And if it's valid, consider choosing a function f and trying to compute this and seeing if you're able to. It might be a complicated integral to solve. And if this is an invalid setup, how would you correct Chang's setup to give the correct bounds for a triple integral in this situation? Finally, just to practice switching the order of integration, here's a triple integral with an order of integration dz, dy, dx already chosen. And the question asks you to rewrite this in the order dx, dz, dy. Thanks for tuning in. Oh, by the way, here's a picture of the region, but you should be able to draw this, at least draw the xy plane region to start with and try to reparameterize this in terms of other variables. Thank you for tuning in to all of these videos. It's been a pleasure teaching this class through the video lectures, and also it's been really fun in class working with all of the groups and the whole class together. So I'll see you next time, not in a video, but to finish up our last class for 6.4. Good luck on your exam and good luck with the rest of your career at Emory.